Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1892 marks a pivotal moment, a transition from the classical to the modern, heralded by Hendrik and Antoon Lorentz's seminal work, The Theory of Electrons. This essay endeavors to explore the genesis, content, impact, and enduring legacy of this foundational contribution to physics. Before Lorentz, physicists navigated a conceptual terrain fragmented by the disparate domains of mechanics and electromagnetism. The reigning paradigm, formulated primarily by James Clerk Maxwell's elegant equations, effectively described electromagnetic phenomena, yet it lacked a fundamental understanding of the nature of matter and, critically, the interactions between matter and electromagnetism. Maxwell's equations, though powerful, existed as a set of mathematical entities disconnected from any concrete physical reality at the atomic level. The prevailing view posited a continuous, ether-filled space as the medium for light propagation, a concept that, while facilitating the mathematical description of light, failed to provide a physical model that integrated electromagnetism with the emerging understanding of atomic structure. This fragmented understanding presented a profound challenge to the scientific community of the time. Lorentz, building upon the foundations laid by Maxwell and others, sought to unify these disparate domains. His genius lay in proposing a model where electricity and magnetism manifested as interactions within a framework of charged particles, laying the groundwork for the modern theory of electromagnetism. The prevailing scientific climate, even before Lorentz's work, exhibited a growing interest in the properties of matter. Experiments with cathode rays, conducted by scientists like William Crookes, hinted at the existence of charged particles. This nascent awareness of the electrical nature of matter provided a critical intellectual impetus for Lorentz's work. He recognized the potential of linking these observed electrical phenomena with the established laws of electromagnetism. The theory of electrons, in its essence, posited that all electromagnetic phenomena, including light, are caused by the behavior and interaction of these fundamental charged particles, specifically electrons. This was a revolutionary departure from the prevailing ether theories. The core tenets of the theory, initially presented in a series of publications, proposed that matter comprises electrically charged particles, which he termed electrons. These electrons, capable of motion, interact with each other and the electromagnetic field. The interactions between these particles, governed by Maxwell's equations, could explain all observable electromagnetic phenomena. Lorentz introduced the concept of a luminiferous ether, a hypothetical medium that permeates all space but whose primary function was to act as a coordinate system for the propagation of electromagnetic waves, rather than as a passive medium. He also meticulously described the forces acting on these electrons, particularly the force exerted on a charged particle moving in a magnetic field, now known as the Lorentz force. This force, expressed mathematically as a relationship involving the charge, velocity, and magnetic field strength, became a cornerstone of electromagnetism. He further introduced the concept of the electromagnetic mass of an electron, noting that the inertia of a charged particle would increase as its velocity approached the speed of light, a significant step toward understanding relativistic phenomena. The immediate impact of Lorentz's theory was profound. It provided a unified framework for understanding electricity, magnetism, and light. Predictions derived from this model, notably concerning the interaction of light and matter, found immediate experimental verification. One of the most striking early successes was the explanation of the Zeeman effect. In 1896, Pieter Zeeman, a Dutch physicist, experimentally observed that a spectral line emitted by an atom split into multiple components when the atom was placed in a magnetic field. Lorentz, upon learning of the experiment, swiftly applied his theory to explain this phenomenon. His detailed calculations, based on the interactions of electrons within the atom interacting with a magnetic field, correctly predicted the polarization and the frequency splitting of the spectral lines. This successful prediction was a powerful validation of the electron theory. The Zeeman effect provided direct experimental support for the existence of electrons and confirmed the validity of Lorentz's model. The successful prediction bolstered his theory's credibility, transforming it from a promising theoretical framework into a compelling explanation that captivated the scientific community. The impact of the theory of electrons extended far beyond its immediate successes. It became a foundational work, influencing generations of physicists. Its influence, however, was not without its challenges. The concept of a luminiferous ether persisted, but its interpretation changed. Lorentz initially envisioned the ether as a stationary medium, but in time, the implications of his theory, particularly concerning the velocity of light, led him and others to reconsider this assumption. Further developments extended the theory, eventually leading to Albert Einstein's special theory of relativity in 1905. Einstein, deeply influenced by Lorentz's work, built upon the foundations of the electron theory while discarding the concept of the ether. He adopted Lorentz's equations for the transformation of space and time, notably the Lorentz transformation, and reinterpreted them, leading to a new framework based on the principle of relativity. Einstein, rather than accepting the ether's existence, proposed that the laws of physics are the same for all observers in uniform motion. This perspective, which eliminated the need for the ether, revolutionized our understanding of space, time, and electromagnetism. Several individuals and works demonstrably influenced the creation and conceptualization of Lorentz's theory. Foremost among these were the works of James Clerk Maxwell. Lorentz utilized Maxwell's equations as the foundation for the electromagnetic interactions in his theory. The mathematical elegance and predictive power of Maxwell's equations were integral to Lorentz's approach. Also contributing crucially were the experimental findings of earlier scientists. The observations of the cathode rays, which demonstrated the existence of charged particles, motivated research and provided initial evidence for the existence of electrons, influencing Lorentz's atomic theory. The work of George Fitzgerald, who proposed that moving objects contract in the direction of their motion, further fueled Lorentz's explorations into the behavior of electrons, especially at high speeds. Fitzgerald's hypothesis proposed that the length contraction could explain the null result of the Michelson-Morley experiment, strengthening Lorentz's model. The influence of the theory of electrons extended in myriad ways, shaping the development of modern physics. It provided the theoretical framework for understanding electrical conduction in metals and the behavior of semiconductors. Its ideas informed early quantum mechanical models of atoms and molecules. The concept of the electron, central to the theory, became a fundamental particle in the standard model of particle physics. This concept continues to shape our current understanding of the nature of matter. The Lorentz force, derived from his theory, is an essential concept in the study of electromagnetism and finds application in diverse areas, including the design of particle accelerators and electric motors. The Lorentz transformation, initially developed to explain the behavior of electrons, became a cornerstone of special relativity. The theoretical and experimental successes spurred further exploration into the nature of electromagnetism, opening avenues for research. Despite its significant achievements, the theory of electrons encountered criticism and revisions. One significant challenge was the concept of the stationary ether. Though it provided a useful mathematical framework, it contradicted experimental results. The Michelson-Morley experiment, conducted in the late 19th century, failed to detect any motion of the Earth relative to the ether, challenging the basic premise. This null result, initially unexplained, led to the development of hypotheses, including Fitzgerald's length contraction. Lorentz ultimately revised his theory, incorporating the length contraction and time dilation, features that became central to Einstein's special theory of relativity. The theory did not fully address the structure of the atom. Though it correctly described the interactions of electrons with electromagnetic fields, it did not offer a detailed explanation of how electrons are arranged within an atom, opening the possibility of further research. The inability of the theory to explain the stability of the atom in the context of classical electrodynamics posed a challenge until Niels Bohr's introduction of quantum mechanics. The reception of the theory of electrons was overwhelmingly positive, though marked by certain initial criticisms. When first published, it was widely lauded by the scientific community. It unified seemingly disparate concepts and provided experimental verification. However, certain physicists, recognizing the limitations of the underlying framework, questioned the necessity of the ether. Einstein's formulation, dispensing with the ether, ultimately resolved this problem by providing an alternative perspective based on relative motion. Over time, as experimental evidence mounted, the theory gained wider acceptance, becoming an integral part of the physics curriculum. Lorentz himself remained active in the field, contributing significantly to the development of physics throughout his career. He received the Nobel Prize in Physics in 1900, jointly with Peter Zeeman, for their work on the Zeeman effect. This recognition cemented his position as a foundational figure in the history of physics and highlighted the lasting impact of his contributions. The lasting legacy of the theory of electrons is immeasurable. It provided a foundational shift for understanding the nature of matter and electromagnetism, paving the way for the development of modern physics. It laid the groundwork for special relativity, provided a deep understanding of electromagnetism, and introduced fundamental concepts like the Lorentz force, which are still in use across various fields. Its contributions to our understanding of light, electricity, and magnetism are essential to numerous technological and scientific advancements. Lorentz's work, with its emphasis on the electron as a fundamental entity, continues to shape our understanding of the universe at the most fundamental level. The work stands as a testament to the enduring power of theoretical insight and the transformative capacity of scientific inquiry. The theory, despite refinements and reinterpretations, remains a cornerstone of modern physics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.